morning, Vietnam. Boy, I'd always hope to say that someday and actually be able to mean it. This is Xavier Prochaska from UC Santa Cruz, where it's 9 p.m. Joining FRB 2021 for plenary session 6B. If that's not what you expected, then find another place to hang out. You can call me X. As a member of the SOC, I love the idea of these 12-hour dual sessions. Just didn't realize I'd be running the graveyard shift, but hey, who am I to complain? I think our fearless leader has slept about 2.5 hours over the last 3 days. I think it's no wonder he insisted on a 4-day rest break, which he fully deserves. Everyone give it up for DJ Hessels. Who knows what ungodly early hour it is in his household. He'll be spinning our greatest hits from 12 hours ago, straight from YouTube tonight. Although I expect we have a live presentation or two as we go. With that, we're gonna jump right in. Charlie Kilpatrick will be our first presenter from Northwestern University, who will be presenting on constraints and optical counterparts of fast radio bursts. If you have questions, hit me up in the Q&A or on Slack, which I'll be monitoring as we go. Charlie, take it away.
Great. Okay, I'm really excited to be here, and thank you so much to the conference organizers for putting this together. I feel like I've learned a lot, this being my first, big FRB conference, and there have been a lot of great talks so far, especially on the radio side. But I'm very honored to be able to kick off this multi-wavelength session and tell you a little bit about the work that I've done as a postdoc at Northwestern University and in collaboration with the F4 collaboration. But I'd also like to recognize that we wouldn't be able to do this work without really the great scientific input from FRB collaborations like Chime and Craft, and some of this work was done in collaboration with both of them. So without further ado, this is specifically on optical counterparts to FRBs and constraints on transient counterparts. So we've heard a lot about this, and I won't really belabor, why multi-wavelength too much, but as we've heard multiple times now, radio bursts are cheap. And there's a rich body of literature just describing all of the many progenitor systems, and in particular emission models that can cause these. But the counterpart models at shorter wavelengths can vary wildly. And so I think that gives us a lot of great leverage on what progenitor systems, and again, emission models exactly are producing the radio bursts. And that's really the kind of angle that I like to look at FRBs from. And of course, we've heard as well that there might be multiple populations of FRB progenitors. They span a very wide range in injected energies and luminosities, and just the environments and distances at which we've seen FRBs, all the way from the galactic magnetar, of course, to the most luminous and distant bursts. So I'd like to think just about all the possible progenitor models and what counterparts they might have. And I think just looking at this large population as a whole, and constraining what counterparts we can, even if some of them are intrinsically rare, can give us a good angle on really getting to the bottom of this progenitor problem. And just going in a little bit deeper into the galactic magnetar, sort of our forlorn hope is this X-ray counterpart that we've seen both in integral and CONUS wind that's also been discussed. But this also tells us a lot about what we might expect to see at other wavelengths, and in particular the optical. So of course we've heard about the synchrotron maser, which predicts some emission in the optical. Magnetars, as we know, come directly from core collapse supernovae, which, despite the fact that G57.2 is likely over 10,000 years old, of course, supernovae produce the luminous optical emission and perhaps persistent emission long after that. And so, we'd really like to constrain at all time scales and in all ways what counterparts we might expect to see. And so the optical provides really a rich body of literature in theory and observations, and in particular of sources that we know are counterparts to neutron stars like short gamma ray burst, kilonovae, like we've heard about in the previous sessions. Not shown on here are fast blue optical transients and luminous red novae, all sources that we might expect to be associated in some way with FRBs. And so this is really my goal, is to be able to constrain at all time scales, and in particular these very short time scales, what we might expect to see right before or right after a fast radio burst occurs. So there's really three strategies that I've tried to organize this into in ways that I think about constraining these optical counterparts to fast radio bursts. A lot of people have looked into coincident imaging just in really the large amount of survey and archival data that we have, just because optical surveys are conducted all the time and image the entire sky down to relatively faint magnitudes every night. And these, of course, can constrain bursts on timescales, or optical counterparts on timescales of days to years of a burst. So getting to these more slowly evolving counterparts. I'm also engaged with more reactive follow-up. So immediately succeeding a burst, we've been able to trigger follow-up on timescales of minutes, and extending to within days of a burst, which again can constrain some of these same counterparts, but getting more into the regime of the extremely fast varying optical counterparts. And then, of course, the vast majority, I think, of the multi-wavelength follow-up has just been pointing at repeaters, and that's yielded a lot of the most interesting scientific results that I'll get to a little bit at the end. So thinking about these coincident sources or coincident imaging and survey data that we've been obtaining just all the time in the optical. So the transient name server, which mainly catalogs optical transients, but it now, of course, is cataloging a lot of the chime sources, is a great repository of well-known bona fide optical transients. And in the future, surveys like the Large Synoptic Survey Telescope is going to obtain a lot of data and really dwarf the size of these catalogs, and enable us to associate possibly optical counterparts with fast radio bursts that are occurring every day, like in the chime catalog. But you know, I've been wanting to think about just you know, what is the best strategy to use to perform these associations, as it was done recently, just using the Zwicky transient facility with the repeating FRB 180916 and looking at coincident optical transients. And you know, really, this is sort of a numbers game where better localization and time constraints can give you a handle on what optical counterparts like supernovae and these fast blue optical transients might be associated with bursts. So just as an exercise, I've been taking the entire chime catalog and cross-matching to sources in the transient name server, and doing this with a graduate student at Northwestern, Vic Zhang, who's really becoming an expert at this. But even with the relatively coarse localizations that chime has, we're able to you know, very precisely say that only a handful of optical transients could be associated with these bursts. And even beyond that, in F4, we're using the dispersion measure constraints in conjunction with the Marquardt relationship, and in work similar to that that's been done in the past with F4 to be able to constrain the likely volume in which these bursts are happening. So even further narrowing down what optical transients could be associated with bursts. So you can imagine doing this on the fly with every single burst that occurs in the future, and with a very large number of transients that are going to be discovered, for example, with LSST, But of course, really the problem here is the probability of chance coincidence. And of course, it's impossible for both of these transients to be associated with the FRB. So, what do we really need to be able to say just on the fly, what is an optical transient that we really think with high probability is associated with a burst? Well, just with an on-the-fly equation and calculating the supernova rate within sort of this volume that I'm using for a chime-like burst, we would expect about 55 supernovae per year per degree squared. So getting our localizations down to about 1/10 of a degree squared or better, as I knew a lot of groups are already doing or will soon be capable of doing, will yield exponentially better association between the large body of optical transients that we'll soon have and the FRBs that are being discovered every single day. So just moving on to the more reactive or follow-up that we've been doing in F4, we've been using a lot of telescopes all around the world to perform rapid targeted follow-up. And of course, this is difficult because it's hard to get onto a telescope, on the timescales that FRBs occur over milliseconds. But with follow-up on the timescales of minutes to hours, and especially using the FRBs occurring in the local universe at low DM, as we're finding more and more of, we'll be able to constrain these fast blue optical transients, kilonovae, neutron star-like counterparts, as well as the sort of luminous red nova models that I'm hoping we'll hear a lot more about in a future talk. But to hear more about this and the follow-up that we've done so far, I really encourage you to look at Consuelo Nunez's poster on follow-up that we've done of 8 FRBs on sort of short to moderate timescales. But we currently have a program now using Las Cumbres Observatory, and we're trying to get this follow-up down to within minutes or even faster to seconds using rapid TO time. And that's really possible because Las Cumbres Observatory, of course, has global coverage. And so an FRB in principle that occurs anywhere in the world, especially say in Canada or Australia, where a lot of our searches are occurring, will have coverage on the ground in the immediate aftermath and can slew a telescope immediately. And we found that we can get follow-up within at most 5 minutes of a burst. But to do this effectively, we really need a reaction system and rapid alerts. So low latency alerts, VO events that we'll be able to react to on the optical side.
Charlie, 3 minutes.
Okay, great. So finally, I just like to talk about really, I think where some of the most promising follow-up has done. So pointed monitoring of repeaters, and especially our favorite repeater, FRB 180916. We've been able to obtain a lot of lucky observations like we did last year, almost exactly a year ago, with the 4-meter APO telescope, where we obtained follow-up within 2.2 seconds of the burst as we were basically just sitting on it. And so these provided some of the deepest constraints on a synchrotron maser counterpart. We were able to rule out significant parameter space just down to extremely deep magnitudes using this 4-meter telescope on second timescales. But stay tuned to the next talk to hear about very interesting constraints on even shorter timescales using a larger aperture telescope. So we're able to rule out, for the synchrotron maser model specifically that I think is very promising, parameter space just using this one very lucky observation. And so I think this is a promising method, especially again with these low DM bursts, where we'll be able to say, is this model consistent with what we're seeing? There are a lot of caveats to this based on the size scales and where the source of the emission is exactly. But I think this is going to be probably the way of the future for, at least for optical follow-up. And then finally, I know this is an optical talk, but we're continuing this sort of lucky monitoring follow-up, just sort of pointing and praying with NuSTAR and XMM Newton on September 14th and 15th. This will be the most sensitive hard X-ray observations to date of FRB 1809-16. We welcome collaboration from anyone, especially with radio follow-up, but really any multi-wavelength searches that want to perform observations on these dates with us. And so with that, that's the end of my talk. I'll just throw up my conclusions and take any questions.
Thank you, Charlie. Thanks for that outstanding overview and whirlwind of optical counterparts and the tantalizing high energy observations you've got forthcoming. Charlie is online, roughly 11 o'clock or so there in Chicago area. So if you have a question for him, please type it in the Q&A or type it on the Slack. I am checking both. I'm not seeing anything in the Q&A, but I suspect it's probably mine. No questions in the Q&A. Slack, anyone wishes to pester Charlie before he heads off to sleep? Here comes one from Ryan Shannon. Charlie, do we expect a change in radio optical efficiency as burst luminosity increases?
Yeah, that's a great question, Ryan. I mean, the model that we've been using for most optical bursts don't predict any significant change in the fluence ratio from the radio to the optical. But that's entirely relying on the synchrotron maser model that we use specifically for the APO observations. So obviously, the beginning of my talk, we referenced other models, and especially on shorter timescales that we're going to hear about in the next talk. So I think this is really a systematic effect, sort of a model-dependent effect that I think we're going to need better constraints on the progenitor model and the emission model before we can say more about that.
Great question. Thanks, Charlie. Other questions for Charlie Kilpatrick and optical counterparts to fast radio bursts? Definitely an area that's going to be leveraged, I think, quite significantly as we go forward. Checking Slack, not seeing in there. Charlie, thank you so much for staying up.
Yep.
We appreciate it. Appreciate the talk. Get some sleep.
Thanks, X.
And see you next week on FRB 2021. Seeing Ryan reminded me that I hear from the craft Slack that Ryan Shannon has set the over-under on when I'll fall asleep at 9:45 p.m. local. My wife says to take the under, but remember, this is only an exhibition. This is not a competition, so please, no wagering. Next up tonight, we've got Nicolas Tejos joining us, recorded from Chile, the Universidad Católica de Valparaíso. Nicolas is going to be presenting us on high-cadence optical limits on the repeating FRB 1809-16. Nicolas, take it away.
Okay, so thank you very much. Hi, everyone. I am Nicolas Tejos. I'm a professor at Universidad Católica de Valparaíso in Chile. I'm going to be presenting results on high-cadence optical limits on the repeating FRB 1809-16. This is work done in collaboration with Time, but as part of the F to the 4th team. And in particular, I highlight here the contribution of Prochaska, Consuelo Núñez, and Charlie Kilpatrick for this particular observations I'm gonna present. So yeah, the outline of the talk is the following. I'll start with a brief motivation. Then I'm going to present the experimental design and the particular observations we use. Explain the target a little bit, why we chose it, the optical imager we use, which is called Alopeke in Gemini North, that reaches 10 millisecond timescales in the optical cadence, and also comment about the time coincident pulse during the time of the optical observations. So the results, I'm going to present briefly the results, which are non-detections of optical counterparts from which we can place upper limits that might be interesting for constraining theoretical models, which I briefly mentioned in the implications. I'm going to finish with a summary and conclusions. So the main motivation is, of course, have observational data that might be able to constrain theoretical models for the engine mechanism of fast radio burst, and in particularly to perform high cadence millisecond optical follow-up of fast radio burst. As has been nicely reviewed in the last days, and also by Charlie in the previous talk, there are several models that predict emission at shorter wavelengths than radio, and that includes the optical. Some of these models are synchrotron masers or magnetar flares, but there might be others as well, and depending on different models, predicts different intensities of the optical counterparts. However, as far as I know, no associated optical emission has yet been observed, and this corresponds to timescales of seconds, days, months, or years. And of course, those searches are also subject to small samples and strong selection biases. But still, people have been looking for optical counterparts, and none has been found so far. One of the main problems in the optical searches is the cadence of the observations, because even the shortest ones, like seconds, that we are used to in the optical community, at least in the extragalactic optical community, is large compared to the millisecond timescale of the FRB pulses themselves. So perhaps a new alternative for continuing this optical monitoring is to go to the millisecond timescale as well. And that has been done, for instance, in the past by the work of Hardy et al. 2017. However, those limits were not constraining because of the FRB that they chose to follow and the optical aperture that they used. So the question remains whether there are or not optical counterparts, and we want to try to answer that from the millisecond timescale perspective. So the experimental design and the observations, we will closely follow the work of Hardy et al. 2017. They observed FRB2021 with a 2.4 meter telescope, Thai National Telescope, and the ultraspec instrument, which reached a cadence of 70 milliseconds. So we want to repeat the same experiment, but with a larger aperture, with a higher cadence, so 10 milliseconds, and also choosing a closer FRB so we can put stringent limits because the FRB will be closer. So the target that we chose was the closest known repeater FRB at the time that we performed the observation. That's FRB 180916, also known as the repeater 3. It's located about 150 megaparsecs away, and it has a well-established period of 16 days approximately. It's also important for this kind of observations to have a well-localized FRB, because the typical field of view of the fast camera imagers are small, so we need to know exactly where to point the optical telescope. So this is the target we chose. Then the camera, I'm going to explain a bit about the instrument we use in the optical. It's called Alopeke. It's in the 8-meter Gemini North telescope in Hawaii. So the design is very compact, it's very simple, and it has two cameras, a blue and a red camera, from which you can choose different filters independently. And there are two main modes, speckle mode and wide field mode. Speckle mode has a very narrow field of view, but so you can resolve, you can reach the close to the diffraction limit in the optical. And the wide field mode, which is the one we're going to use, it has a wider mode, larger pixel size. But here we are not interested in resolving, especially the FRB. We just want to measure any possible flux. So we chose this one based mostly to increase or decrease the cadence, so go to 10 millisecond cadence. For that, we chose the wide field mode with 2x2 binning, pixels twice that size over there, with a region of interest smaller than the 60 arc seconds to also reach a faster readout. So with that setup, we can reach 10 millisecond cadence approximately in the optical. The instrument has a suite of different filters to which we can choose from. And in this particular observations, we chose R filter for the blue camera and the I filter for the red camera. And we have those two observations simultaneously taken. So we coordinated these observations with time because, of course, we wanted to make sure that at the time we were observing in the optical with Gemini North, time was operative. And we also coordinated it to coincide with an active period of the FRB 1809-16, predicted by the 16-day period. And that the observations happened in October 2020, last year. And we were lucky. Well, I'll show you that there was a time pulse at the time of observation, so that's important. Here is the field of view in the optical based on a GMOS Z-band, and the Alopeke field of view is the dashed square. So this is how a single 10 millisecond image look from the Alopeke perspective. And it's important also to have a wide field of view because we have some reference stars that are useful for calibrations. Okay, as I mentioned, there was a pulse observed by time at the time of the Alopeke observations, signal to noise of order of 12, fluence 4.4 Jansky millisecond. And this is the waterfall plot. What I wanted to emphasize here is that the typical pulse, so the pulse of the actual, the width of the pulse detected by time, it's of comparable time span as the cadence we reach in the optical. So that's interesting. So we know, so the experiment, it's as follows. We take several of these images. We register count at the FRB position. We know exactly where to look within the field of view, and we do this in the R filter and the I filter simultaneously. Then we use, for instance, this reference star provide relative astrometry and relative photometry to know to convert counts to flux and to know exactly where to look for within the field of view. So here is results of the observations. So in the y-axis of these plots, we have counts per exposure. Each dot is an individual Alopeke exposure, so one of these images, and at the position of the FRB. And we see that it fluctuates around a mean. The FRB arrival time is given by the shaded region. It has an uncertainty, mostly given by the accuracy by the timestamps of the instrument Alopeke, which is about 160 milliseconds. So we know at some time within that range the FRB should have arrived, but we don't know exactly where. So we look at the region. And this is how assuming in the set of exposures look like. As you can see, there is no excess of counts closer or within the expected arrival time in either of the cameras. If we zoom out for all of the observations we took, about 200,000 frames, 100,000 in each camera, we see that there is no excess of counts anywhere close to the FRB coincident with FRB. So from this non-detection of transient optical, we place upper limits based on the counts. Also, yeah, the counts are well behaved in the sense that are following a Gaussian distribution around a mean. We check that, and there are some fluctuations, as you can see, some decrease that and changes as a function of time of the counts. That it's due to weather conditions and systematic about the reading of the instruments, which we can handle very well because we have the reference star that give us a reference to compare with. So here I show you the blue camera counts compared to the reference star counts in the blue camera, scaled by 1/6, so we are in the same panel, and we see the same typical fluctuations happening in the star and the FRB position count. So we don't find this to be associated to the extragalactic sky. It's systematic from the atmosphere or of the instrument. Yes?
3 minutes, Nicolas, sorry.
3 minutes, okay, thank you. So the same you can see here in the red camera. So now, so the implications of this, so we place upper limits on this eta parameter, which we follow from Chen et al. 2020. So eta here will be the ratio between the fluences, the integrated fluences in the band, in this case optical and radio. So which goes close to the specific fluences in the optical times the frequency in the optical divided by the frequency in the radio times the specific frequency in the radio. So based on that, we set 3 sigma upper limits for the specific fluences in the optical of about 8 to the 8 times 10 to the minus 4 Jansky millisecond, or 7 depending on the band, which where we compare with the fluence in the time pulse. We can place an eta upper limit of the order of 100. This number needs to be revisited more closely, so that's why we say this is preliminary. Placing this limit in a wider context, here we used a figure adapted from 2020. So the allopec limits will be here. Here is the y-axis, the eta parameter in different wavelengths as a function of frequency. And our current allopec limits are constraining compared to other previous experiments done in the optical, and might be interested for ruling out or exploring progenitors of the emission of the FRB pulses. Okay, so let's finish with the summary and conclusions. I have presented high cadence optical high cadence optical observations at the order of 10 milliseconds using Gemini North allopec instrument on the repeating FRB 180916. Optical observations were coincident with the time FRB pulse at the time. We obtained 100,000 exposures in each filter, R and I filters in the optical, and we didn't see any bright optical emission coincident with the FRB. So we place upper limits based on these non-detections, which imply an eta value in the optical smaller than 100. So this upper limit will disfavor some of the proposed theories of FRB emission mechanisms. Of course, just in the last 30 seconds I have, want to just say that this is only coming from one set of observations, one pulse, so we are not really ruling out etas at this value yet. We want to repeat this, and we have a plan ongoing in the context of the F⁴ collaboration to repeat this experiment with the same repeater in 2020B from which, if we are lucky, we might place more stringent limits, especially if we have a brighter FRB pulse coincident with those observations. So stay tuned, and thank you very much for your attention.
Thank you, Nicolas. Wonderful talk. Nicolas is asleep at this hour, so he has asked that we ask him questions via Slack. Please post anything you have for Nicolas in the Plenary 6 channel. Casey Law is online, I see from a discussion of panelists, but we will show his recording and then he will take questions live afterwards. So you're welcome to type those in the Q&A on the Zoom or in Slack, and I'll read them from either spot. Casey, take it away. Oh, wait, let me introduce the talk. Casey Law from Caltech, member of the DSA and Real Fast Collaborations, and he'll be presenting some really exciting results on the FRB and PRS populations. Casey,
thank you for the opportunity to speak today. Really great to be here. So I'd like to talk to you about sort of a study or consideration of populations, both on the FRB side, but with a particular focus on these persistent radio sources, so PRS. You'll hear that a lot in this talk. The idea is to try to use PRSs and treat them as sort of a first-class, aspect of the FRB population, and thinking about them from that perspective, and help us understand the nature of FRBs. So I'll open it with a provocative statement, which was not mine, but there's nothing as useless as a radio source is a sort of famous quote from Jim Condon. And that would be a pretty insulting thing to say if you weren't Jim Condon, because he is a pioneer of measuring radio sources through sky surveys. And the point, of course, is that you measure when you make a measurement in the simplest sense, it's a flux and a position, at some radio frequency. And you might measure something, and then you don't know if that radio source corresponds to a radio star that's up in your backyard, sort of a few parsecs away, or a supermassive accreting black hole at the edge of the universe, right? So it's really hard to say physically what's happening just from measuring a radio source. That's Jim's point, and he spent his career certainly thinking about how to make use of them. And the argument I'm making here today is that associations are really when we start to get something of value from measuring radio sources. And we've already heard great presentations in the meeting so far, and we'll hear some more. But spatial associations, if they can be done robustly with a low false association probability, can tell us incredibly, far more information than the radio measurement alone. So environment, tells us the context for the object. So what star formation rate of the host galaxies, is it forming in a globular cluster, and what kind of things live in globular clusters? We've heard about those things. And session 9 will have a lot more on the host galaxy question. Birth event. So if we can tie FRBs, or specifically, any radio source in general to some birth event, like a supernova. We heard Charlie talk about that, and that could be a real breakthrough because we know a lot about how, say, a supernova behaves. And so that gives us a lot of contextual information to understand the radio emission. And then third category would be, what comes later, right? So after the birth event, there's some remnant object, whether it be a black hole or a neutron star or some sort of plurionic emission from a nebula, say. And these things, again, we understand them in some broader context, physically what's happening, and then we can interpret the radio emission in an appropriate way. So I'll just make one other note is that, these questions that I'm going to talk about today with persistent radio sources and the population are really important to understand the source question, right? What is the source that makes FRBs, or the sources? But it's also really important to use FRBs as probes, which is one of the sort of long-term goals of the field. If you'd like to use dispersion measures, scattering, propagation effects to talk about the intergalactic medium, host environments, and so on, we really at some point really need to know very precisely what the environment in the local environment of an FRB is, and how to separate that from propagation effects that are of more relevance to, say, cosmology. So I think the question of associations and understanding the source model has short-term value and long-term value. So when we talk about persistent radio sources. So, the radio source that's associated with a fast radio burst, we have a name for that. We call it a PRS. It's, again, it has incredible value once we identified it as being associated with FRB, because we know FRBs are an incredible mystery. And now we have this peculiar radio emission that's persistent, that is located within, say, a parsec or so of this source of these luminous bursts. And so the archetype of this combination FRB PRS source is FRB2011-02, which by coincidence was the first one localized. It turned out to be extremely valuable for understanding and modeling the nature of the environment of that FRB. Subsequent observations found that it was extremely magnetized plasma that was associated with the environment of the FRB, and we can characterize the spectrum and do modeling of that. There's still ongoing work with time evolution of the PRS and all sorts of great stuff we can do. That constrains things like the energy, the age of the environments that's formed the FRB. So there's just really a lot that came out of this one identification of just a radio source, right? As this uninteresting thing, because it's associated with the FRB. Now, those were the sort of the heady days, because it seemed so peculiar that we thought, in fact, there's a nice paper by Ternay Eftekhari who talked about what would happen if we had 10 more localizations. If they looked like this in terms of their host galaxy, in terms of their association with persistent radio sources, perhaps you would have solved the origin question for FRBs, within a few years. Now, in fact, we know today it's, we've done more of those localizations. We have more information, and if anything, the question is diverged, right? We have not converged. We have a more diversity of hosts, and there's there is not in the subsequent, say, 20 localizations or so of FRBs, and ones with good associations with host galaxies and environments, deep radio imaging. We have a diversity of contexts and associations. So this is just a kind of a highly biased sample of sort of VLA localizations. The top row shows the VLA image. The middle shows the VLA deep image, usually from commensal data at the same time. And the bottom row shows optical follow-up, showing host galaxy and other environment of the FRB. So diversity of hosts and associations. But one exciting thing that's come out recently is was hinted by Reshma Anna Thomas in her polarimetry talk on the first day, which is FRB190520. We'll hear more about it from Dee Lee in a breaking news talk, I hope, at the end of the conference. And I won't go into in great detail other than to say that it is remarkably similar to FRB2011-02. And so you can see that we have a localization, we have a persistent radio source, which we can say with great confidence is a compact, co-located persistent radio source with the FRB. And then we have a relatively diminutive sort of host galaxy. And so in many ways, we consider 190520 to be a clone of 1211-02. So that raises a whole host of questions. I think, first of all, it sort of elevates the question of PRS again. It makes it relevant to revisit and think about that 1211-02 in the broader context, and really treat the PRS as a fundamental aspect of the lives of at least some kinds of FRBs, right? So some of them have this association, and it's pretty important and informative to understanding the origin question. So that's the context for what I wanted to talk about today. So the rest of my talk, I'm going to go through our sort of study of archival data and collating results from papers and sky surveys to try to constrain and talk about correlations between properties of PRSs and FRBs and what that means for the population. So the motivating questions are, how common are PRSs and FRBs? So we used to sort of think that it was a pretty rare thing, but now we have two examples. So we're going to dive into a bit of that question. What is the fraction of FRBs that have PRS emission? Two, how are FRB and PRS properties correlated? So that's another interesting thing to talk about. It tells us something about why we have PRS emission, potentially. And third, can we find PRSs without FRBs? PRSs are luminous radio sources. Maybe we can turn the problem around and start to look for PRSs instead of FRBs. So to do this in a meaningful way, I think we need to step back a bit and think about what we mean when we say FRB and PRS. So we have a good sample of localizations, and so we can start to say things and discuss things in sort of physical units rather than observationally convenient things, which are, say, fluences. And so there's always a bit of a choice, a balance between, when you define what FRB means and what PRS means, you have to balance between what measurements exist and what's convenient and what's useful. I will propose some definitions, and people are free to choose different ones, but I find these to be useful. So my definition for the purposes of today is that a FRB is a radio transient with a luminosity, particular luminosity of 10 to the 29 ergs per hertz, greater than 10 to the 29 ergs per hertz, and a timescale which is much faster than a second, presumably, being inclusive of the microsecond, nanosecond scales that we've heard discussed here. The point is that it's a coherent process that is extremely energetic and detectable at cosmological distances. Repeater in that context is just more than one, right? We get more than one from the same source, then we call it a repeater. And then third, this one's maybe the most open to interpretation and discussion, but I'm going to argue that a persistent radioluminosity of 10 to the 29 ergs per second per hertz is an appropriate definition for a PRS if that source is directly associated with an FRB. And when I say directly, I mean we can just clearly say that it's not related to, say, star formation in the host galaxy, and that it is spatially coincident with the FRB. That's very clearly been shown for 12102, and I think we will ultimately show that well for 1905-20. So just some quick notes based on those definitions. Maybe this is where people get sensitive to it. we can discuss in Slack. STR 1935 is an FRB, but not a repeater. That's just how it turns out. I'm open to discussion. And FRB 2011-24A has no PRS because it has persistent radio emission in the host galaxy, but not a PRS. So when if you take these definitions, then you can consider where the PRSs are and where we know there are no PRSs according to that definition. And so this is a plot that shows radioluminosity detections and limits for the sample of localized FRBs, right? So we know roughly where the distance is for these, and we know limits on the radio brightness associated with them, so we can put limits in most cases. And some of these are limits from, say, sky surveys, like the VLA Sky Survey, or RACS from ASCAP. And what's surprising is that in many cases, we don't have very good limits, in fact. So that horizontal line shows the 10 to 29 value, and 2 points with circles and stars show the detections, and all the other points show upper limits. So the points that are below the line that are upper limits are formally called, have no PRS association. The labeled points are actually repeaters. That's another thing I should say. So some repeaters have good limits, some don't. Some non-repeaters have good limits and some don't. And so we can sort of categorize things. And I thought it was appropriate to use sort of a Venn diagram. I'm not going to fill it in because I just want to sort of lay it out here, but I'll fill it in a second. So, there's a great big circle outside of this, which is all FRBs, and there's a subset of those which we know to be repeating, and there's a subset of all FRBs which we know to be localized well. Those tend to overlap a little bit. There's this LPRS circle, which is that subset of localized FRBs which are have meaningfully constrained PRS emission. It's also smaller than the number that's localized. And then there's finally the smallest circle shows the detections, the number of PRSs measured. And so if you fill in the numbers, it looks something like this. The numbers might change a little bit depending on your definition or how you count limits. But broadly speaking, we have about 20 to 25 localized FRBs. Most of them are non-repeaters, and then there are about 5 localized repeaters. Some of this I should say is as work in prep and will be submitted in the next week or so. So I apologize for that. And so 2 of the repeating FRBs are localized and have PRS emission. 8 of the localized, yes.
Oh, sorry, just 2 minutes. My apologies.
So eight of the FRBs are localized with non-repeaters. And so broadly, the answer to the first question I raised is you can just sort of, if you take this as an unbiased sample, it's the ones that we were able to observe, 15% of FRBs have a persistent radio source. And here's some names if that's helpful. I'll give you some sense of what we're talking about. So the second question is, are there correlations between FRB properties and PRS properties? So you'll note that 2 of the 5 repeaters have PRSs. You can estimate the true probability, the true distribution of PRS fraction as a function of we'll see. So if you treat it as a coin flip, biased coin flip problem, is a binomial distribution with a true PRS fraction. And the measurement of 2 of 5 gives you a constraint on the probability of that true fraction. And so you can do this for the repeater and non-repeater fraction. And in fact, it looks like there is sort of some evidence that PRSs prefer to be with repeaters. There are potentially some biases in how that sample is defined, and that's certainly worth scrutinizing carefully. But I think we have some weak evidence potentially that there is a distinction between where PRSs like to live, which correlates with FRB activity and repetition. I'll skip this slide for interest of time, but there's potentially evidence, that some FRBs have very high anomalous local DM, and that may also be a prediction, suggests that some sources might have a persistent radio source associated with them, which would be consistent with some models of how FRBs form and what their environment is like. And then final point, which I'll try to squeeze in, is finding PRSs without FRBs. So we have a pretty good idea of what the FRB all-sky rate is. So it's actually pretty comparable to the core collapse supernova rate, which is a fun fact, 10 to the 5 per cubic gigaparsec per year. You can then, if you have an estimate of the mean repetition rate per FRB and an estimate of the beaming fraction, so how many of them are beamed in our direction, you can actually back out the true source density, right, in terms of sources per gigaparsec. And so Liam Connor is a collaborator on this. He had some nice ideas for using the CHIME catalog release to sort of bound the repetition rate, sort of assuming that either all FRBs are repeaters with some power law distribution of repetition rates, or that there's truly non-repeating and repeating events, and then taking a mean of those 2 populations and calculate a gross repetition rate. And so with those bounds in the rate, we can then back out, with an assumed beaming fraction, we can back out the true source density. And it's a pretty wide range, but that number is it's a physical density of sources in the sky, right, in the local universe. So that's, to my knowledge, that might be one of the first constraints on that density of sources of FRBs. And then one more leap, which is that we can take this fraction of sources of FRBs with PRSs, and we can then calculate the density of PRSs in the sky. And so if you push that through, you can get an estimate of how many sources there are within some volume of sky that you were sensitive to, say with a sky survey. And there's something like potentially thousands of PRSs that are in this VLA sky survey. So when you look at these flux density distributions, like say when people on the left panel, bottom panel, there's this distribution of flux density used for cosmology and other applications. There's bright sources tend to be attributed to AGN. The fainter sources correspond to, say, star formation activity. And those are like the 2 main categories of sources that you see in the extragalactic radio sky. And what I'm arguing here is that there's probably, maybe a few percent of those sources which are in fact something that could be totally different, right? It could be a PRS driven by some really, new phenomenon. And so that's something I'm pretty excited about exploring and finding independent of the FRB question. And I'll just note that these PRSs are often offset from the nuclei, and so they are distinguishable from AGN, which is the dominant population. So I think it's an exciting potential exploration for sky surveys in combination with FRB science. So I will close with this slide, and I'm at the end of my time, so I will stop and take questions here. Thanks.
Excellent. Thank you, Casey, for that provocative presentation, which I know inspired a bunch of discussion already on the Slack, but I see we have more. I believe one of our panelists has a question for you who will be presenting momentarily. So maybe let me pass her the mic and ask it live. How novel.
Thank you. Hi, Casey. Thanks for that talk, and thanks for, I'm sure it's very late for you. With these persistent sources, can we tell what they are? So they're not the AGNs, but like, what else do we know about them? Thank you.
Yeah, thanks for the question. I think FRB2021 probably has the best theoretical modeling and constraints because it is observed really well, and there are some pretty specific, models that are described in great detail. But there's also great radiopolarimetric work that just helps us understand both the density of the plasma and the magnetization of the plasma. And so many of the models, I think, tend to converge on an idea that it's some compact object like a neutron star that is energizing this through some sort of spin down magnetic power of the neutron star. But there also are models related to like ULXs, where you could have an accreting black hole that can also generate the same kind of plasma through different effects.
Thank you.
Additional questions for Casey? You can hit me up on Slack. Checking the Q&A, nothing in there at the moment.
Can I ask a quick follow-up?
Please.
Yeah. So, Casey, do you think it's possible that the PRSs are just showing us what might be a typical environment for some repeaters, in the sense that that they're perhaps not really directly related to what creates the emission, but that one is finding in low metallicity environments, kind of nuclear star forming like regions, we're finding an IMBH that's accreting in a dwarf galaxy, and that's a persistent radio source, and we're finding the FRB is very close to it spatially, because there's local star formation there producing really extreme magnetars, but really that the two aren't really physically related in any other way than you have a nuclear star forming region.
Right. Well, so I guess one constraint is that there's spatial association through VLBI, as you know well. So that associates FRB to PRS to within some very tight constraints, but certainly that size constraint is it still allows for, say, the environment or a binary system potentially, or a cluster environment, that something happening in that context could be indistinguishable from an individual FRB PRS source model. I think binary models are particularly interesting in this context potentially, because they add a lot of physics, right? So there's an orbit, and there's interaction, and there's potentially some sort of secular evolution of the star and the binary. So maybe that's part of your question potentially is.
Yeah, I think that the VLBI constraints are still consistent with the idea that the PRS is not necessarily like a nebula or something around the source itself, or that it's intimately related to the emission mechanism, like you might expect, say, like in a ULX type model or something like that. I think there's still some room for it to be kind of like the galactic center magnetar in our own galaxy, that you just have a source that's in a nuclear star forming region. It has a high RM because of the environment that it's in. You see this compact radio source because there is some low level accretion onto in this case, intermediate mass black hole. That it's more a reflection of the type of environment in which the source is forming, as opposed to very directly related to the emission.
Right. Like, so I guess the luminosity of the radio emission is pretty large, right? So I guess the argument would be that the environment where FRBs are found is also an environment where you tend to have accreting, supermassive black holes, right? So.
Well, yeah. So if it's sorry to interrupt, but like if it's an IMBH, the radioluminosity is not such a big deal. If it's a nebula around a neutron star, it has to be 500,000, 1 million times more luminous than the Crab Nebula, so it becomes pretty spectacular.
Yeah. So I guess the question is it causal, or is it environment? Yeah, it's a good question. I don't know the answer. it's nice if you can cinch it all up into one model, of course.
Agreed.
That's not the way the universe always works.
Excellent. Great discussion. Casey, we've hit the 10 o'clock hour. I think you may go to sleep. Thanks for staying up and joining us.
Thank you.
And I'm pleased to introduce our first live presentation of this 6B, Jielai Zhang from Swinburne University and the Australian Research Council Centre of Excellence for Gravitational Wave Astronomy, who will be presenting on the Deeper, Wider, Faster program and simultaneous imaging of FRBs and many other wavelengths. Please, the floor is yours.
Thank you. It's really great to be here to talk to the FRB community. When I entered transient astronomy very recently, about 1.5 years ago, and FRB 2020 was like an introduction to this world for me, and it was a very nice welcome. So it's great to be here to talk about 2 FRBs detected during the Deeper, Wider, Faster program. So my talk will have 3 parts. The first part will be very short because this is an FRB conference and people have given great backgrounds already. The second part will be to describe what the Deeper, Wider, Faster program is all about. And then thirdly, tell you about what happened during the September 2020 DWF observing run. So as we all know now, FRBs have been only detected in the radio wavelengths, although I saw on Slack there's a bit of discussion about whether this galactic magnetar constitutes as an FRB. So I think that's a very interesting discussion. Nevertheless, it's a very important thing to search for multi-wavelength counterparts because many different models will predict emission at other wavelengths. Other than this galactic magnetar, we've found no FRB counterparts despite a whole host of different searches that was mentioned in the first talk today. This is a non-exhaustive list and includes studies to look for afterglows, coincident in space and time searches, as well as associations with other types of transients such as gamma-ray burst, gravitational waves, superluminous supernovae, to see if they're related or not, but it's all yielded nothing. This particular galactic magnetar was very exciting to see that a magnetar can give a radio burst that's almost as bright as the extragalactic population. And this kind of study, as well as the talks we've heard today, points to the importance of having telescopes on the same field of view at the same time with a radio telescope in order to find a counterpart in another wavelength. And that's what the Deeper, Wider, Faster program is all about. Before I go into its details, let me introduce you to the team. The PI is Jeff Cookie, who's also at Swinburne. Our team has 2 PhD students, Sarah Webb and Simon Good. Sarah is graduating this year. 3 postdocs, myself, Dougal Dobie, and Anais Mahler, and past team members include Igor and Tyler. The Deeper, Wider, Faster program coordinates observations with multi-wavelength telescopes to simultaneously observe the same field of view. And we're interested in not just fast radio bursts, but also other sub-second to hour timescale transients such as supernovae shock breakout, kilonovae, flare stars, gamma ray bursts, to name a few. This kind of transients that have timescales that are really fast cannot use a follow-up strategy to catch coherent emission, but of course, counterparts to FRB may happen an unknown amount of time before, during, or after the radio burst itself. For the Deeper, Wider, Faster program, I will briefly talk about some of the main telescopes we use for simultaneous observing. In the radio, we've used the Parkes radio telescope, or otherwise known as Muriang, as well as ASCAP and Meerkat. In the microwave, we've used the South Pole telescope. The infrared is our weakest link right now. There isn't currently available a wide field deep infrared telescope, but some are coming online, which is exciting. In the visible, we typically use the CTIO 4-meter telescope, the DE-CAM instrument, but we've also used Subaru before. In the ultraviolet, we use the AstroSat Indian Space Telescope. AstroSat also has X-ray capabilities. In the X-ray, we've used the Chinese HXMT InSight Space Telescope, and in the gamma ray, SWIFT. So the Deeper, Wider, Faster program coordinates all these telescopes around the world as well as in space to observe the same field at the same time before anything has happened, but also during, see that little lightning there, as well as after. This is very different to follow-up observations, as many people have already pointed out in even this session. And it's important to do this simultaneous observing because, for example, for the galactic magnetar, X-rays can arrive tens of seconds before the radio signal if it's emitted coherently. And associated bursts in other wavelengths can be like a long time before or after the FRB burst as well. So yes, we just point all these telescopes at the same field of view at the same time and wait for events to happen. And so in order to maximize the volume probed, we use the largest apertures with the largest fields of view possible in all the wavelengths. Of course, it's often a trade-off. Typically, our fields of view are degrees across. So our main optical telescope, which is DChem, on the CTIO 4 meter is 3 square degrees, and that's shown in the background there. Parkes has a very similar footprint. The Molonglo radio telescope is this oval here. The South Pole telescope is also very well matched in field of view. SWIFT, HXMT, AstroSat, ASCAP, Pierre Auger, some of the other telescopes we've used have fields of view that are larger than shown in the figure. And that's what deeper, wider, part of deeper, wider, faster is. So since we point and stare and wait, field selection is really important. A strategy that people have talked about often already is to look at an FRB repeater. So that's something we do as well. We look along low extinction lines of sight because otherwise optical telescopes will be heavily hampered. And one thing that actually turned out to be a little bit difficult is the ability to do simultaneous observing with multiple telescopes coordinated at the same time. So we spend a lot of time calculating what we can actually see with all these telescopes. To this point, I would like to advertise some work done by an internship student that worked with me at the end of last year, Andrews Dizidoza Manuel. He's a master's student at Northwestern University in South Africa, and he wrote a bit of code where you can take in information of 2 telescopes and the period of time that you want to co-observe with those 2 telescopes, and plots the amount of co-observability time for any RN deck during that time. And we've used this to figure out what fields are observable by our coordinated telescopes. So deeper, wider, faster. What is this faster about? Faster is about, as you probably guessed, the fast cadence for finding fast transients. But it's also fast processing of data to discover transients quickly in order to do fast follow-up. And the deeper, wider, faster program actually has 4 parts. And mostly so far, I've talked about this first part, which is simultaneous multi-wavelength observations, but there's 3 other parts. The second is to do real-time data processing and transient detection. This happens within minutes. This happens within minutes. The third part is to do rapid response and conventional target of opportunity observations, and this happens via our DWF partners and collaborators who are willing to give us telescope time, as well as a whole bunch of proposals that we write many times a year. This follow-up happens within hours to next day. We also have a program to do long-term follow-up, and this is to follow the long-term time evolution of any slower evolving transients that we find, as well as to follow up on host galaxies, because the deeper, wider, faster program loves fast radio bursts, but we also observe other transients that may be slower evolving, like kilonovae, supernovae, and such. All right, so the September 20 Deeper, Wider, Faster program, we had, outside of the core team members, we had a whole bunch of people join us, but I'll just highlight some students. Vivek Gupta, who gave a talk earlier in the week. Sarah Caddy is a PhD student. Junho Kim is also a PhD student at Seoul National University, and Junmo Kim is about to start his PhD. So watch out for them. In September 2020, the Deeper, Wider, Faster program observed 2 fields. We had 6 half nights of simultaneous coordinated observing, and we looked at 2 fields per night. And that means we looked at each field for about 2.5 hours each. I will just focus on one of the fields. Both fields were in the southern hemisphere. You can see in this galactic extinction map, the Milky Way, as well as the Large and Small Magellanic Clouds. So one of our fields was pointed at the repeating and localized FRB 1907-11, and it's in that field that we observed 2 FRBs, but neither of which were from the repeater itself. This gives a timeline of the observations that we did. Time on the x-axis, and on the y-axis are all the different telescopes that participated. HXM, the blue colors are the high energy ones, green are the optical telescopes, and radio are the red are the radio. In the optical, we had time on the CTIO telescope, but unfortunately due to COVID, it was offline. The 2 black lines indicate the times where the 2 FRBs were detected. I'll call this FRB1 and FRB2. So this is FRB1, and it was detected here. In the background is a KMT-net optical image. The repeating FRB.
Jielai, you've got about 3 minutes. Sorry to interrupt you.
Thank you. The repeater is right here, and the first FRB1 was found here. It had a signal to noise about 10, and the dispersion measure is not quite, but similar to this FRB here. FRB2 was found here, and also with a dispersion measure that's not too far off from the repeater. What's interesting is in such a small field of view now, there's 3 FRBs, although just 1 has been seen to repeat. And we're doing some work to try and see if this is like a cluster environment or not. One interesting thing to point you to is for FRB2, which is a very high signal to noise FRB of a signal to noise ratio of 100. There was a signal to noise of 7 radio short signal coincident with it, as well as an unclassified transient within the error region. Although it's not sure if the lowest signal to noise signal was, it could be just noise, and this unclassified transient was only observed once, so we don't really know what it is or if it's related, but interesting to point out. To put you out of your misery, we did not find an FRB counterpart, but I would like to briefly say how difficult it is to coordinate so many telescopes to try and find counterparts. So for FRB1, HXMT was over something called the South Atlantic anomaly at the time of this FRB, which means that data was not usable. Our main optical telescope was broken for 6 minutes, exactly around the time of this FRB, and our other optical telescopes did not have this FRB within its field of view. On the last day, all of our optical telescopes were weathered out. However, we were able to get coincident in time observations with our high energy telescopes. This shows a timeline of, on the x-axis again, and all of the flux density upper limits that we measured. So in the optical, we were able to go to about 7 times 10 to the minus 6 Jansky. Our exposure times were 1 minute. And so it doesn't give us the best upper limit. And in the X-ray, we were able to get an upper limit with the best upper limit came from Ashler Sats using a 10 millisecond binning of one of the instrument's data. we were able to monitor the field afterwards, specifically using Meerkat, but no repeat bursts were found, and a bunch of optical telescopes were following along too. I think so the Deeper, Wider, Faster program has been awarded a 3 years long-term time on the CTIO 4-meter telescope. So we'll be doing this every semester. Hopefully we'll be looking at this field again in September. Hopefully we find something again. In the infrared, where our weak point is, the Roman Space Telescope and the Prime Telescope are coming online soon, which will be very exciting. And our collaborators continue to work with us to do this simultaneous coordinated observing. I mentioned that KMTNet in our September run had 1-minute exposures. With CTIO, we can do 20-second exposures. And in the future, Huntsman telescope will join us with CMOS cameras to do sub-second imaging as well, which will be very exciting. So the future is very bright. Hopefully, at some point, we will have more than upper limits. Thank you.
Thank you, Jielai. That was wonderful. Really enjoy the DWF project. If you have questions for our speaker, please type them in the Q&A or on Slack. I'm going to start us off with one of my own, which is, how can interested listeners join in on the DWF effort if they wish to bring to bear their own telescopes?
Yes, so feel free to contact me. You can message me on Slack. We're very happy to have people join our observing runs. For example, as you saw, even though we tried so hard with 4 optical telescopes, none of them were coincident in time. And so having telescopes in different locations really helps in case of weather and things like that. So yeah, feel free to reach out. I'm also, any help from theorists to interpret limits, including having simultaneous multi-wavelength limits instead of one wavelength limit other than the radio. How can we best use that? Any advice on that is also very welcome, because I'm not very good at the theory side of things.
Sounds like a good shout out to the theorists to join and gather town at some point. When you said September, one of the precise days of that next DWF run?
We'll be observing September 5 to 10.
Wonderful. Checking Slack. It's been very quiet in Slack today. I guess this crowd likes to watch it live. That's great. Well, thank you very much for the presentation, and good luck to DWF. I'm sure you'll catch just what you're hoping for, hopefully in September.
Thank you.
Very good. Our 5th presentation and penultimate, I think that's how we say it, is from Sibasish Laha of Goddard and the University of Maryland. I believe we'll be catching this one on recording. The title is The Simultaneous Fast Nicer Campaigns of the FRB 12-1102. And DJ Hessels, please spin the track.
So thanks very much to the conference organizers to give me the opportunity to talk. I am Sibasish, and I am a Swift mission scientist at NASA Goddard Space Flight Center. And this work is based on multi-institution, multi-wavelength collaborations throughout the world. And a special thanks to the FAST team, the NICER team, and the SWIFT teams for their support and help during the analysis. And I must mention that this is an ongoing work, so it's the results are the final results are still being worked up. So I'll talk on about FRB 180301, where we have the NICER and fast simultaneous observations, and also FRB 180916 using Swift BAT observations. So the last year's paper by Luo et al. Using fast observations found that the polarization angle changes have been detected for 180301, which implies a magnetospheric origin with more efficient radio emission from a magnetar, if it is a magnetar which is creating the FRB. And for FRB 121102, there hasn't been detections of any polarization angle changes, which may suggest that relativistic shock models are the reason for the emissions. So this prompted us to observe these two sources simultaneously with a fast telescope in radio, with a NICER, which is soft X-ray instrument on board the International Space Station, simultaneously in these two wavelength bands. So FAST, as we all know that it's the largest single-dish radio telescope and very highly sensitive for FRBs which are very far away. For example, these two sources are technically around 1 gigaparsec away from us. And we report only the FRB 18031 in this talk, as FRB 121102 work is still underway. And hopefully in the next few weeks, you will see the publication in the archive about these sources. So about the source 18031, it is around a gigaparsec away, and it's repeating, but apparently not periodic. It has a high degree of linear polarization, similar to 121102, but it shows polarization angle swings. And the previous detections from this source has shown the peak radio flux densities range from around 5.3 to 94.1 millijanskis. And the burst rate is around 1.2 per hour during the bursting period. And its extremely high brightness requires coherent radiation models. We conducted simultaneous observations of FAST and NICER. It happened on 4th, 9th, and 19th of March. FAST detected 6 bright bursts during these observations, and 4 of which happened to occur during the NICER observations. And the radio burst peak flux densities ranged from around 28 to 96 millijanskis. And the burst widths, time widths ranged around 1 to 5.52 milliseconds. And the burst fluences were around 27 to 170 milliseconds. And all the bursts were above 10 sigma, signal to noise. So NICER is a very unique instrument. The full form is Neutron Star Interior Composition Explorer. It is on board the International Space Station, and it is a non-imaging X-ray telescope, which means that it's just a photon bucket, and it has a very high effective area. And the most important criteria it has is the microsecond time resolution, and which is very, very important in constraining the neutron star equation state and other properties. So, and it operates in the 0.2 to 12 keV, and it's very unique to study the FRBs in the sense that FRBs happen in millisecond timescales, and this gives us a unique opportunity. Unlike, for example, Chandra does not have this timed resolution, for example. But the downside of a non-imaging X-ray telescope is that the background is not determined well, in the sense that unlike Chandra or XMM, where we have imaging telescopes, we have the background well determined. Even a few photon counts from Chandra is a detection. In NICER, it's not imaging, so we have to model the background. We have to estimate the background from known background sources and background events that can happen due to high energy particles striking the detectors. So the NICER observations and data reprocessing were done with standard steps, and also we have taken extra cautious steps regarding the elevation angle, the bright earth limb, so that no extra spurious counts happen in our events. And also we have taken steps to filter out the South Atlantic anomaly, which the telescope, actually the ISS, goes through the SAA quite a few times a day. And these are regions of high energy particles, and they give you huge number of counts in the detector, which are not or not actual source photon counts. So so we filtered very carefully, but still we detected wings. I'll show you the light curves. We still detected wings in the light curve due to improper SA filtering, and we have to be careful about chopping off the data. And the radio bursts happened, 2 of them happened during the wings. So if we include the wings, the net count rate is kind of slightly larger. It's 1.2 counts per second. And if we get rid of the wings, it's around 0.69 counts per second, which is standard NISO background counts. And we used this standard background counts for upper limits. And the spoiler is that we don't detect any X-ray counterpart during these observations. So, and the NISO background background has been used, determined using both the models provided by the NISO team. One of them is the NISO background estimator, and another one is the NISO BACGEN 3C50. So we have done both ways when we saw that our data is background dominated. So this is NISO observation 1, which is a few hundreds of seconds, around 700 seconds. There is no FRB during this observation. But in the second run of the observation, is the 9th of March, we find 3 bursts during 2 bursts happened during the NISO observations, and one of them falling in between when it was within the SAA. And all of the radio times are de-dispersed arrival time at infinite frequency. And we have matched this with the NJD-TDB so that we are observing the right time from the radio and the X-rays. And the last run for NISO happened on 19th of March this year. And fortunately, 2 bursts happened, bright bursts happened as detected by FAST during the NISO observation. The radio time is dispersed again. And you see that the wings that are coming up is because of the SAA, the South Atlantic anomaly. And we have to get rid of that while estimating the right background. So I'll give an example of like how the background spectra, the time integrated background spectra would look like. It's around few kiloseconds background spectrum. So this is the source plus background, and the top one is the calculated background spectrum. So we see that the background spectrum is actually dominating. The modeled background is more than, the predicted background is more than actual source plus background that we observe. So it's completely background dominated. And we don't detect any source counts. That's what we mentioned, at least, in a time averaged way. And NISO is the only X-ray telescope with such a large effective area and with a millisecond microsecond time resolution, I should say. So I have binned it in millisecond bins per millisecond, and you can see that it's kind of, the background shows off clearly that it's background, and there is not much of emission during the FRB bursts. So these are radio bursts 5 and 6. We don't see any excess emission above the background. And we are actually currently looking into, we are currently working into putting strict upper limits on the Poisson and non-Poissonian fluctuations around the detection times. That will give us a very strong upper limit on these X-ray photon counts. And for example, if you zoom into like the actual millisecond time bin around radio burst 5, and this burst actually happened over a time period of like 2.5 milliseconds, we see that the count rate is consistent with 0. At least there is no excess emission which is apparent above the background. And so we don't, technically we don't detect anything, but we have to we are in the process of simulating the upper limit using the Poisson fluctuations, and we will quote some values in the next few weeks. But to give you a handle on what exactly we have measured, is we have X-ray flux upper limits on the persistent flux, which is around integrated over 2 kiloseconds, is around 7.5 10⁻12, which gives us an upper limit of the luminosity, 8.48 1044. Assuming no intrinsic absorption, of course. And if there is an absorption intrinsic to the source itself, then the luminosity will go up. And the typical radio fluence, for example, for burst 5 is around 1 E-19. And typical eta, I mean, which we are still calculating, would be the lower limit on eta would be around 10⁻8. So we are still calculating this, so I have not quoted this. And that's kind of consistent with the other studies in X-rays. And if an SGR 1935 type event happened at 1 gigaparsec, definitely NICER would not be able to detect such an event happening at that distance. I mean, the expected X-ray fluence would be of the order of 10⁻14, which is much lower than, lower than what NICER can detect. So the next thing we want to...
Sorry, 3 minutes.
Okay, next thing we want to ask is, can we rule out magnetar giant flares? Technically, yes, in some sense, because typically considering 1806 type flares up to 1047 arcs per second, if we put it at 1 gigaparsecs, we would expect a flux of 8.8 E-10, which is technically detectable by NICER, but we don't detect any. In line with the polarization angle measurements of Luo et al., we think the magnetospheric origin is more favored for this FRB, where the radio efficiency can be much higher than the X-ray emission efficiency. I'll just briefly mention about the Swift BAT view of 180916. I think Aaron will talk more about Swift BAT event files, data files for FRBs. What I'll talk here about is 180916, FRB 180916, which is at one of the most nearby FRBs at 140 megaparsec, has a period of 16.35 days and a burst rate of 2. And this is a very interesting source because Swift actually, the burst telescope surveys the sky most of the time whenever it's looking at other sources. And this survey data is very crucial because it has a very nice localization, and you have a 300-second integrated time spectra from these data sets. And these are all available in HISARC. And this BAT is one of the only among the few hard X-ray telescopes currently working. And this is a very crucial energy band for galactic, giant magnetar flares. And for example, like the flares from SGR 1935 and 1806 has been detected by BAT, but these are all galactic magnetars. I'm talking about extragalactic sources. But even then, it's worthwhile looking at the BAT observations. So the motivations is, during the burst storms, the magnetar persistent X-ray emission flux can increase by orders of magnitude, and it may take months to years to recover the pre-outburst levels. And the second motivation would be the magnetar giant flare, consisting of like 1047 arcs per second spike, followed by softer pulsating tail, can last up to several minutes. And these are all very interesting emission in X-rays, and hard X-rays, I should say, which could be detected by Swift BAT. And we have analyzed around 250 such observations. All are like integrated over 300 seconds or more. And so typical spectrum would look like this. And I should say that BAT is a very unique instrument in the sense that it's a coded mask imaging, where you have the spectrum, the background is well estimated, and it gets, you can subtract very easily. And this is a background subtracted spectrum, and you don't have to deal with the background. And we don't see any signal above the background. That's what we find. And for all of these observations, we have done this spectral analysis, and we have used the background variance, the 5 times the background variance, to estimate the 5 sigma upper limit on this flux. And The typical 5 sigma upper limit is 7e minus 10 over integration time. So, this is not as strong constraints as obtained from Chandra, but these are definitely consistent with those obtained by other instruments. And the conclusions are, we can possibly rule out energetic giant flares, which dominate around like few hundred seconds and a luminosity of 44 to 47 seconds, and the pulsating tails. And we can also rule out any persistent emission with that upper limit of luminosity. And these disfavor shock models that are more efficient for X-ray emission and favors magnetospheric radio emission from like holomagnetars for this FRB. And to mention, like these are consistent with previous works with other X-ray instruments by Scholz, Berman, Tavani, Pilia, and other authors on this source. Thank you very much, and stay tuned for more results on these FRBs with NICER and SwiftBAT.
Very good. I'm confident that Dr. Laha is asleep over there in Maryland. So if you have questions for him and his really novel experiment, please type them into the Plenary 6 Slack channel, and I am sure he'll answer them when he wakes up. We will conclude section Plenary 6B with a final talk by Aaron Tohuvavohu of the University of Toronto, who is going to discuss digging for high energy FRB counterparts in BAT-GUANO. A clever acronym.
And
please take it away.
now in full screen.
Thank you. Yeah, okay. So thank you very much. My name is Aaron Tohuvavohu. I'm a PhD student at the University of Toronto. I'm going to be talking about searching for high energy counterparts to fast radio bursts, both prompt emission in hard X-rays and gamma rays, and also afterglow-like emission on the order of tens of minutes after the burst in X-ray and UV. And this work has been done with a bunch of people, some of whom are shown on the screen. Jimmy Delaney is a new postdoc at Alabama. He just got his PhD at Penn State, and he's done a lot of the work that I'll be talking about here on the statistics and search techniques that we are, brand new ways of analyzing BAT data. Jamie Kenna at Penn State, we built the whole operations chain for this, and Casey Law and the VLA Real Fast team and Andrew Zwanago with the Chime FRB team provide our triggers and did a lot of, work getting us the triggers that are so critical. So I have to thank Charlie and the other previous speakers in this session for hopefully motivating why you would care about multi-wavelength searches for FRB counterparts. I'm not gonna really try and motivate it that hard because they did a great job. But what I will say is that there is a reason why we want not only to look for multi-wavelength counterparts, but particularly in the GRB or SGR or X-ray flare, whatever you want to call it, regime. And there's various reasons. Many cataclysmic progenitor scenarios predict high energy counterparts, whether they're prompt counterparts or afterglows. And the only EM counterpart of a putative FRB to date was an X-ray flare or a GRB. And this is very important, and it motivates, I think, searching for more of these. But in particular, we cannot just depend on the searches that are currently running in order to find these, and that's because they're faint. SGR 1935 flare would not be detectable by conventional means beyond about 25 kiloparsecs. That's the X-ray flare coincident with the FRB 2004-28. Even magnetar giant flares are very difficult to detect extragalactically. They're bright, but most detectors won't see them beyond about 10 megaparsecs. And then what we found from the joint work with gravitational waves and GRBs is that while classically we detect these cosmological GRBs with EISOs of something like 10 to the 51 ergs, the local population of GRBs, which are much more likely because of selection to be off axis, are substantially fainter by maybe 4 orders of magnitude. So GRB 170817 isn't detectable classically beyond 50 megaparsecs without targeted searches. So this is hopefully motivating why we want to, 1, look in the X-ray and gamma ray regime, and 2, do sensitive targeted searches. And I'm going to argue that Swift is the best instrument to do this with. Swift is a space observatory for people who aren't familiar. It has 3 instruments on board. There's the Burst Alert Telescope, the BAT, which we've heard mentioned by Jielai, and then Sibasish was talking about it just a moment ago. It has a 7,000 square degree field of view, and is the highest effective area GRB mission and most sensitive GRB mission in current operation, and also crucially the only one that regularly localizes GRBs to arc-minute precision. And then also on board Swift are two pointed narrow field of view telescopes, the X-ray telescope and the UV optical telescope. And I'm going to be talking about using all of these instruments today, but focusing on the BAT. So the BAT, as Sibasish referenced, is a sort of unique instrument. It's a coded aperture telescope, so gamma rays cannot be focused. And if you want to get localization, one of the only ways to do this is to basically use the dark arcs and code your detector plane via a shadowgram. So the detector plane is about a half a square meter, and then 1 meter above it there's a coded aperture mask, which is 50,000 holes. Half of them are filled with lead and half of them are empty. And if a gamma ray source shines on the mask, it casts a shadow onto the detector. And if you arrange the lead tiles in your mask in a smart way, you can break all of the shadow degeneracies and uniquely encode different shadows for any possible arrangement of gamma ray sources on the sky. And then you take your observed shadowgram and you deconvolve it or cross-correlate it with your mask, normally by a fast Fourier transform, and reconstruct a sky image. And this is the way that coded aperture imaging has been done for the past 40 years, and for the past 17 years since Swift launched, and it's been very successful. As I mentioned, the Swift Burst Alert Telescope is the most sensitive GRB detector in operation, and intrinsically can detect GRBs farther than any other facility, or X-ray flares or SGRs or whatever you want. With the event data, the time tag event data, so this is each count detected by the detector, tagged with 100 microsecond resolution timing, an energy, and a spatial location on the detector, you can perform really sensitive GRB searches. You can get about twice as far detectability range for GRB 170817 like bursts. You can detect SGR 1935 like flares. We simulate to about 80 kiloparsecs, which is substantially farther than any other instrument, and magnitude giant flares like SGR 1806 minus 20 out to 40 megaparsecs. So this is very important. And crucially also, the arc-minute localization, the very high effective area matters obviously for increasing your range, but the arc-minute localization is very important for two reasons. One, if you localize your GRB to arc-minutes, you can rapidly do follow-up without having to do wide field searches of the localization region. But two, also the FRB rate is sufficiently high that there will eventually be a FRB in close temporal coincidence and agreeable spatial coincidence with, for instance, a Fermi GBM GRB. You're seeing a typical Fermi GBM localization region in pink on the bottom panel. And that will be a chance coincidence. And that's just because the typical GRB localization regions are very large. And the arc-minute localizations from BAT are the only way to sort of break these and do much more sensitive searches that don't have to deal with quite a high chance coincidence rate. But we have a problem. The data that allows all of that awesome science that I was just talking about to be done intrinsically doesn't classically actually make it to the ground. The Swift mission was designed for prompt detection and localization of bursts, which means, in order seconds, which means the only thing that was really funded was real-time analysis. So the data had to be analyzed on board. And that meant that, despite this amazing data, one, the BAT effective area is large, so the data volume is very high. And so since there wasn't a requirement to find GRBs in anything but real time, the capability wasn't built to be able to bring all that data to the ground. The antenna that exists on Swift is bandwidth limited, and the onboard recorders are insufficient to record all of this data, all of this time tagged event data, and bring it down to the ground. So all of the science that I was talking about that would intrinsically be possible for on the ground, targeted searches wasn't actually possible. And so the result was that for 15 years, BAT relied on its onboard real-time analyses to find GRBs. It still did, fantastic, amazing science, but the idea of targeted searches wasn't really possible, at least not to the extent that it could be. But similar to the way that there are baseband buffers on FRB instruments, this time-tagged event data is actually stored on board the BAT for about 20 to 25 minutes. You're seeing this on the plot on the right-hand side. This is the time to wrap the circular event data buffer as a function of mission year. And you see that, that the event data still exists before being overwritten for about 25 minutes. And if you can get a command to the spacecraft to save the data before it gets overwritten in the ring buffer and bring it to the ground, then you could do these sensitive searches. But the problem was that the fastest responding that was possible before last year was order 2 to 4 hours. And I would mention that this is faster than anyone else, but still not sufficient to bring this data to the ground. So we worked really hard on this problem. And the answer is something called GUANO, the Gamma Ray Urgent Archiver for Novel Opportunities. This is the first ever autonomous and on-demand commanding of a space telescope for scientific purposes. It now regularly, about 5 times per day, autonomously commands Swift in extremely low latency based on external triggers from gravitational wave instruments, from FRB instruments, from other GRB instruments, from neutrinos, to save the temporally coincident event level data. What you're looking at on the left is a plot of the command arrival latency on board Swift. And this includes all latency. So this is minutes from the astrophysical T0. So this includes the time that it takes the triggering instrument, let's say it's chime, to realize there's an FRB in the data, trigger on it, send us the event. We upload the command gets to Swift, and actually it shouldn't say command arrival on board. This is actually the execution time on board. So now we are capable of retrieving this time tagged event data. We can do the interesting science. And there's also other things that we can piggyback on it to do in terms of TOs, and I'll talk about it in a little bit. But one of the problems that we realize is that this conventional coded aperture mask imaging technique that I was describing before, where you cross-correlate your detector plane shadowgram with the mask pattern, has a problem. And that's that it has a very large image noise population. You're looking at a cumulative distribution of the number of image blips. So this would be like candidate sources in a sky image that's created via the cross-correlation of the shadow mask, as a function of the signal noise. And you see about signal noise of 6.5 or so. There's a kink in the distribution where it goes from signal dominated, everything above SNR of 7 is essentially real, to a dramatically noise dominated. If you do a log linear extrapolation though, you see that there are certainly real signals hiding in the data, but they're totally dwarfed and unrecoverable. And in addition, conventional imaging rejects uncoded counts on the detector, which contain information. It neglects using the energy information, and also has a lower effective area at high energies, because even lead is transparent to gamma rays above about 200 keV, and so it decreases your effective area to short hard bursts. So Jimmy Delani and I worked on a totally new way of analyzing BAT event data, and this is a maximum likelihood analysis. So instead of taking the data and deconvolving it with the known mask pattern, instead we build a full forward model of the instrument and simulate GRBs through the instrument and compare them to the observed data with a likelihood test. What you're looking at on the bottom of the screen is not real data, it's simulated data for GRBs that arrive from different incident directions on the sky onto the detector plane. This highly coded region that you see on the left is, basically has all of the arc-minute localization information encoded in the rapidly changing response here. But you see that even in the non-coded region, there are shadows of mostly the spacecraft components that are cast on the detector that do have non-zero counts associated with them that contain information that you can use. And imaging totally rejects these and throws them out. And our new nitrate search uses this information to be more sensitive to GRBs, one, and to localize fainter GRBs than could possibly be localized with imaging. And the sensitivity that increase that we achieve is about a factor of 2 to 5. But the spatial parameter space to do these forward models and these likelihood searches is massive. As I said, the BAT field of view is 7,000 square degrees, and the PSF is about 18 arc minutes. So that's a lot of spatial locations to check. And we want to find these GRBs, whether they're GRBs that don't have counterpart, or they're targeted searches in response to FRBs in low latency. So we've worked on a lot of intelligent spatial seeding and stage refined localizations. What you're looking at on the left is the field of view of the burst alert telescope projected onto the sky. These IMX, IMY units are just a tangent plane image projection. 1 unit in these coordinates is about equal to 40 degrees on the sky, to give you a sense of how big the field of view is. And basically each circle is is the location where a different GRB injection was done, and a model shadowgram like one of these produced for a GRB at that location and then compared to the data. But as I said, the PSF is actually a lot smaller than these circles. So we do a first round where we do the spatial seeding to find the best fit localization, which was going to be the reddest regions. And then in the top right, we zoom in on that region and do even more spatial seeding with different resolution grids to sort of try to converge on the best fit localization. And you see that that's what's happening first with these circles, and then with these different coarse grids in the blue dots as a function of coordinates. So these coarse grids are separated by order 20 arc minutes, and then the green dots are coarse grids that's separated by even smaller. And then eventually we converge to the red, which is the maximum likelihood position and also known to be the true GRB position for this case. And
Aaron?
yeah.
3 minutes.
Okay, great. So that took a little bit longer than I expected. I'm sorry about that. I'm going to skip over some things. Basically, the takeaway is that nitrates is much more sensitive. This maximum likelihood switch is much more sensitive than imaging. You see this here with the maximum signal noise ratio achieved by imaging on the left versus nitrates on the right. And you see this large noise population in orange from imaging just totally vanishes. For nitrates, it's suppressed, and the significance of the true GRB position is radically enhanced. The cost is a factor of 1 million in CPU time. But if you think detecting faint GRBs or SGRs or magnetar giant flares is worth it, then you might want to do this. To show you that we can actually, discover real things this way, we've done external GRB searches with guano nitrates now since February 2020, and we have detected hundreds of GRBs with guano and provided unique arc-minute localizations at a rate now of about 1 per month. And this was 15% of all arc-minute localized GRBs last year. And many of these have been these localizations have been independently verified by at higher latency than what we're providing, or I guess longer time scale after we provide the localization by the interplanetary network, or for 6 of those 18, we actually got the localization out quickly enough to discover an X-ray afterglow that confirmed the location. But of course, we're here to talk about FRBs. And so guano now, gets triggers on FRBs, and we've gotten about 300 FRB triggers to date from a combination of Real Fast and Chime. Real Fast started giving us triggers in April 2020. Their localizations are spectacular, but the rate is rather low. And Chime just about 3 or 4 months ago started giving us triggers for guano. We've dumped, about 220, I think, time-tagged event data files around the times of FRBs and run low latency GRB searches around plus or minus 15 seconds of the de-dispersed FRB time. We have the deepest ever upper limits on over 200 FRBs of about 2 × 10⁻⁸ ergs per centimeter squared per second. If anything like the cosmological short GRB population is present in any of these FRBs, it's ruled out. And I should say that this is essentially the deepest GRB upper limits that will be possible until they give us the new Compton. So if you want better, advocate for that. And also the most comprehensive to date. And due to Chime's high detection rate, we'll start to probe subdominant progenitor scenarios, for instance, cataclysmic progenitor scenarios that might contribute only 1% or less to the total FRB rate within the next few months. And we've shown that if and when we find something, we can distribute that information in order a few hours for follow-up. But just to finish up quickly, if you saw this command arrival on board latency that Guano is achieving to bring down the time-tagged event data files for the nitrate searches, we can also now use this new commanding infrastructure to repoint Swift to point the narrow field of view X-ray and UV optical telescopes at the FRB location at low latency. And we've done this now for 6 FRBs landing on target in less than 50 minutes from the FRB time. Typical upper limits that we haven't found anything. Typical upper limits that we've reached are about 3 × 10⁻13 ergs per centimeter squared per second. So this is typically, sensitive enough to find any GRB-like afterglow, even at cosmological distances on these timescales, and 22 AB mag in the UV. As you see from this latency distribution, we can and will get on target faster. The reason that the fastest to date was 28 minutes post FRB is procedural, and we're currently just working out the final kinks, and we should be able to regularly achieve XRT and UVAT on target at order 15 minutes post FRB, and about once per month we should be able to get X-ray upper limits at order 5 minutes after the FRB. And the trigger criteria right now are just FRBs that have less than 10 arc-minute localization radius and are very bright. And this is because we want to sample exceptional FRBs that are either very nearby or luminous. I'm going to leave this up. These are the future or ongoing improvements you can expect: faster notices of GRB detections, faster TOs, public results for upper limits for public FRBs that are not MOU protected. And the takeaway should be that we're close to probing the sub% level of progenitor scenarios for prompt emission, and within a year, maybe even down to the 0.1% level. So if you have a cataclysmic progenitor scenario, we're either going to find it soon or it's not happening. And these are questions for people that I'd like some response from. Thank you.
Well, thank you, Aaron, for a heroic implementation effort and some really cool results already. I believe that ends 6B and the first sub-week of FRB 2021. Jason, correct me if I'm wrong. I will hand it back over to him and head off to sleep myself.
Yeah, we're done.